Hello everybody. In this session, we discuss the construction of attribute control charts. The entire topic is subdivided into the following subdivisions. 1. The control chart for non-conforming units, NP chart. 2. The control chart for fraction non-conforming units, P chart. 3. Control chart for number of non-conformities, C and U chart. 4. Advantages of attribute control charts. 5. An worked out example. 6. Conclusion. Attribute control charts. Generally, control charts for attributes are grouped into the following 4 general groups. The control chart for non-conforming units. One chart is the P chart, control chart for fraction non-conforming units. The other chart is the NP chart, control chart for number of non-conforming units. Second, control chart for number of non-conformities. 1. The C chart, control chart for number of non-conformities. 2. The U chart, control chart for number of non-conformities per unit. Control chart for non-conforming units. Control chart for non-conforming units is used for attribute type of data whenever the quality characteristics observed result in the classification of a product as non-conforming or conforming units. Consider a production process where the items are inspected for non-conforming units. If the records of inspection over a period of time are scrutinized, the fraction non-conforming will show variations. Under conditions of control, the fraction non-conforming readings tend to approach a fixed value provided the number of items inspected is very large. This value to which the fraction non-conforming readings tend to approach is the standard fraction non-conforming or probability of a non-conforming unit from the process. If P represents the probability of a non-conforming unit from the process, the probability of obtaining R fraction non-conforming from a sample of size n is given by the binomial distribution given as NCR p to the power r 1 minus p to the power n minus r. For example, if the probability of a fraction non-conforming unit is 0.01 and if samples of size 50 are taken, it will be seen that the probability of obtaining 6 fraction non-conforming units are noted. It is clear indication that some external causes has influenced the process. We know that the mean of the binomial distribution is NP and the standard deviation is root of NP into 1 minus P. The binomial distribution approximates to the normal distribution in many practical situations, particularly when NP is greater or equal to 5 or n into 1 minus p is greater or equal to 5 within the mean and standard deviations as that of binomial. This property is utilized in constructing charts for fraction non-conforming to know whether the process is in control or not. Thus, when the values of p and n are known, the standard deviations are easily calculated and plus or minus 3 sigma limits from the average provide the basis for judging the process control. This is the basis of control chart for non-conforming units. When the sample size n is constant among the subgroup samples, it is simpler to plot the actual number of non-conforming units rather than fraction non-conforming units. Such charts are known as number of non-conforming units or simply NP chart. When the sample size is not a constant among subgroup samples, we plot the fraction non-conforming. In such cases, we have chart for fraction non-conforming or simply P chart. Control limits, number non-conforming units chart or NP chart. Case 1, when the mean of the population NP from which samples are taken is known, then the UCL is defined as NP plus 3 times root of NP into 1 minus P, central line is NP and lower control limit is NP minus 3 times root of NP into 1 minus P. As we know that the basis for control charts are mean plus or minus 3 times standard deviation. Case 2. When the mean of the population NP from which samples are taken is unknown and P is estimated using the formula P bar is equal to number of non-conforming units in all the samples combined divided by number of items in all the samples combined. Then the UCL is given by UCL is equal to NP bar plus 3 times root of NP bar into 1 minus P bar, central line is equal to NP bar, LCL is equal to NP bar minus 3 times root of NP bar into 1 minus P bar. Construction of the control charts for non-conforming units. Step 1. Preliminary data for construction of number of non-conforming units charts are generally obtained from past records. Collect k samples, say about 25 of size n, where n being the same for all samples, and record them as defined in the following table. First column shows the number of the subgroups, second column gives the size of each subgroup, the third column explains the defectives in each subgroup. Record the total samples inspected and total defectives observed. Step 2. Obtain an estimate of the fraction non-conforming as P bar is equal to number of non-conforming units in all the samples combined divided by number of items in all the samples combined, that is equal to summation di divided by n into k. We have inspected n into k samples. Step 3. Compute upper control and lower control trial limits for number of non-conforming chart as follows. UCL is equal to NP bar plus 3 times root of NP bar into 1 minus P bar, central line is equal to NP bar, lower control limit is equal to NP bar minus 3 times root of NP bar into 1 minus P bar. Step 4. If no sample has number of non-conforming units violating the limits, the samples may be considered homogeneous. Step 5. If condition 4 is satisfied, accept P bar as the standard fraction unconforming. Step 6. If the condition 4 is not satisfied, remove those samples with number of non-conforming units more than CL and compute P bar from the remaining samples. Step 7. Repeat step 3 with the new P bar. Step 8. Compare the number of non-conforming units in the remaining samples with the revised limit. Consider the samples as homogeneous if none exceeds the limit. Step 9. If step 8 is satisfied, accept the revised value of P bar as the standard for process. Step 10. If 8 is not satisfied, repeat step 6 to 9 and repeat as often as it is necessary for it to be satisfied. If more than 25% of the samples get rejected, collected fresh data after exercising technical controls on the process. Step 11. Accept the final values of P bar as the standard fraction non-conforming for the process. Step 12. Compute NP bar plus 3 times root of NP bar plus 1 minus P bar and NP bar minus 3 times root of NP bar into 1 minus P bar using the value of P bar obtained in 11. Step 13. Prepare a chart for non-conforming units with the vertical scale at the left showing the number of non-conforming units and the horizontal scale indicating the subgroups number of samples. Step 14. Draw a horizontal line across the chart at NP bar at the central line together with two broken lines at the control limits at NP bar plus 3 times root of NP bar into 1 minus P bar and NP bar minus 3 times root of NP bar into 1 minus P bar. Step 15. Continue selection and inspection of samples and plot the number of non-conforming units on this chart in the order of production. Mark on the chart any point at which any serious change in the process is occurred. Step 16. The interpretation of this chart is similar to that of charts for measurements. Step 17. If any of the plotted points falls above upper control limit or if a run of points is noticed above the control line or any upward trend is noticed, it should be lead to proper action to set right the situation. It also indicate where chart for average and range should be installed. Step 18. If any point falls below the lower control limit or if any run of points noted below the central line or if any trend is noticed, it indicates improvement in the process provided the standard of inspection has been maintained. Investigations are to be made in such cases to locate reasons for improvement and maintain such conditions. Estimate of the improved standard is to be obtained and control limits are to be revised. Step 19. The principle of rational subgroups mentioned in the case of X bar and R chart hold good in this case also. Control chart for fraction nonconforming or P chart. We know that the fraction nonconforming P follow binomial distribution with the mean and standard deviations are given by P and root of P into 1 minus P divided by n. Obtain the data and tabulate as follows. First column explains the subgroup numbers, second column explains sample size, third column explains the number of defectives. The difference between P chart and NP chart is that in this case the sample sizes are changing from subgroup to subgroup. We have the first subgroup has N1 samples, the second subgroup has N2 samples, the third subgroup has N3 samples, etc., etc. In each subgroup count the number of defectives. Calculate one more column, the last column di by ni, which explains the fraction of non-conforming units in each subgroup. Compute the totals, total number of items inspected, total number of defectives observed. Step 1. Collect K, say about 25 samples. Say the ith sample has size ni, ni need not be same. Step 2. Calculate fraction non-conforming for each sample as Pi is equal to di divided by ni, that is number of non-conforming units in that sample divided by the number of items in that sample. Step 3. Obtain an estimate of the standard fraction non-conforming explained as earlier. P bar is equal to number of non-conforming units in all the samples combined divided by number of items inspected together, that is summation di divided by summation ni. Step 4. Compute control limits as P bar plus or minus 3 times root of P bar into 1 minus P bar divided by ni. It will be different for different samples because the control limits are depending on the ni, the sample size in each subgroup. Step 5. Compare each Pi within its limits. If no sample points falls outside the limits, samples may be considered homogeneous. Step 6. Otherwise, homogenize the samples following the sample procedure as in the previous case. Step 7. Accept the final value as the standard fraction non-conforming p bar. Step 8. Compute p bar plus 3 times root of p bar into 1 minus p bar divided by Ni as UCL, and p bar minus 3 times root of p bar into 1 minus p bar divided by Ni as LCL using the value of p bar obtained in 7. Step 9. Prepare a chart for fraction non-conforming with the vertical scale at the left showing the fraction non-conforming and the horizontal scale indicating the subgroup number of samples. Step 10. Draw a horizontal line across the chart at central line together with the 2 broken lines at the control limits at p bar plus 3 times root of p bar into 1 minus p bar by Ni and p bar minus 3 times root of p bar into 1 minus p bar by Ni. Step 11. Plot the number of non-conforming units on this chart in the order of production. Step 12. The interpretation of this chart is similar to that of chart for measurements. A typical P chart is given below. Unless in NP chart, in P chart as usual we have the central line. The red broken line explains the UCL. The red broken line below the central line explains the LCL. Only the difference between the P and NP chart is that here UCL is not a straight line, it will have up and downs. Similarly, LCL is not a straight line, it has up and downs because the UCL and LCL depends upon Ni. So, that is the difference between P and NP chart, otherwise similar. Here the dots are the points which are fraction non-defectives, not the total number of defectives. So, one more column we have to add in the table, that is Pi is equal to Di divided by Ci should be plotted here. In NP chart we are plotting total number of defectives, that means NP values only we are plotting, that is the only difference between P and NP chart. Control chart for number of nonconformities, C chart. Data obtained in control chart for nonconforming units do not consider the magnitude of nonconformities contained in a time. There are many cases in industry where control of nonconformities is considered important. Examples are nonconformities in casting, imperfections in certain area of paper, imperfections in certain area of fabrics, etc. Control charts for number on nonconformities are usual in these cases. The sample size for the control chart for number of nonconformities is usually fixed on the duration of time, length, area, single unit or group of units. The Poisson distribution generally explains the pattern of variation for the number of nonconformities. If the average number of nonconformities per unit is m, then the probability of getting r nonconformities in any sample is given by exponential to the power minus m, m to the power r divided by r factorial. Let m be the average number of nonconformities per unit for a process. It is possible to calculate the value of r, the number of nonconformities per unit in samples, for which the probability is nearly 0. If any sample unit has more nonconformities than this value, it is a clear indication that external causes has influenced the process. The standard deviation of the process distribution is given by root m. The normal approximation to the Poisson distribution may be used provided m is greater than 5. In many situations, it is possible to arrange collection of data in such a way that the normal approximation could be used. Using above information, limits for judging the process for control could be calculated. Detailed procedure for construction of C chart is as follows. Tabulate the data as below. Subgroup number, the first column, Second column, the number of nonconformities observed in each subgroup. Compute the total number of nonconformities observed as summation Ci. Case 1. Sample size n is constant. Step 1. Collect about 25 samples of size n and count the number of nonconformities C in each sample as explained in table 3. Compute the average number of nonconformities per sample as C bar is equal to number of nonconformities in all the samples divided by total number of samples, that is equal to summation Ci divided by k. Step 3. Compute trial control limit UCL is equal to C bar plus 3 times root of C bar and lower control limit is equal to C bar minus 3 times root of C bar. Step 4. Compare the number of nonconformities in each sample C with UCL and LCL. If no sample has more nonconformities than the UCL or less than the LCL, the samples may be considered homogeneous. Otherwise, homogenize the sample. Step 5. Accept the final value of m as the standard number of nonconformities per unit. Step 6. Compute control limits C bar plus 3 times root of C bar and C bar minus 3 times root of C bar using the values of m obtained in 5. Step 7. Prepare a chart for number of nonconformities per sample with the vertical scale left indicating the number of nonconformities and horizontal scale indicating subgroup of the samples. Step 8. Draw a horizontal line across the chart at m, that is central line, and 2 broken lines at the control limits C bar plus 3 times root of C bar and C bar minus 3 times root of C bar. Step 9. Continue collection and inspection of samples and plot the number of nonconformities in each sample on this chart. Mark on the chart any point at which any change in the process occurred. Step 10. Interpretation of this chart is similar to that of NP chart. Case 2. Sample size is not constant, that is U chart. Tabulate the data as explained below. First column is sample number, second column is sample size, third column is number of nonconformities and fourth column is fraction nonconformities. The difference from C chart to U chart is that here the sample size differs from subgroup to subgroup, hence we are adding one more column, that is computing the fraction nonconformities Ci divided by Ni for each subgroup. Compute the total number of samples inspected, summation Ni, total number of nonconformities observed, summation Ci. Step 1. Construction of U chart is similar to C chart. In this case, the number of nonconformities in the sample is not plotted. Instead, Ui is equal to Ci by Ni is calculated for each sample and Ui values are plotted. Central line will be at U bar, upper control limit will be at U bar plus 3 times root of U bar by Ni and lower control limit is at U bar minus 3 times root of U bar by Ni, where U bar is calculated as U bar is equal to summation Ci divided by summation Ni. The control limits will be varying from sample to sample. Step 2. Procedure for identifying out of control situations and interpretations are similar to that of P chart. A typical U chart is given below. We have the central band, the central line, and upper side broken red line is upper control limit, lower side is lower control limit. Since the sample size is varying, again we do not have a straight line for upper control limit, that also varying from subgroup to subgroup. So, that is the difference between C and U chart, and number of nonconformities are not plotted here. Here fraction number of nonconformities Ci by Ni are plotted, that is Ui values are plotted. So, that is the difference between C and U chart. What are the difference between defects or non-conforming units and non-conformities? A defective is an article that is some way fails to conform one or more given specifications. Each instance of an article lack of conformity to specifications defect. For example, a television set is a defective one as its picture tube is not functioning, or in other words, non-conforming picture tube is a defect in the television set. Every defective contains one or more defects. For example, number of defects in a piece of cloth like improper coloring, improper printing, number of surface defects observed in a roll of coated papers, etc. Advantage of attribute control charts over X bar and R charts. The following are the advantages of attribute control charts over X bar and R charts. Attribute control charts do not require measurements. The skill and effort of measurement required to maintain X bar and R charts. By virtue of not requiring measurements, attribute control charts are more economical and less demanding on inspection time. An attribute control chart can be applied to a number of quality characteristics checked at a workstation, whereas X bar R chart requires one chart for each characteristic. Attribute control chart are less demanding on skills of the personnel collecting data and maintaining charts. The chart can be easily read and understood by online production personnel and hence can act as a self-evaluation of operators. Attribute control chart analysis is easier and simpler in compared to X bar R chart analysis. Most often, data collection effort on attribute control charts is very minimal, since data collected for other purposes can be used for the chart. Attribute control chart information is also useful as quality history and is useful for management information of operating efficiency and of control of operating efficiency. An worked out example. The following data were collected on stub joints in different indents. The following table shows the number of joints welded and number of non-conforming joints. How to analyze this using P chart? Now, the P chart is a suitable chart for this example because observe the data. We have the sample subgroup, there are 21 subgroups, and second column the joints welded, the third column number of non-conforming joints. Observe that the number of subgroups welded in each case is different. So, n is varying and the data observed are number of non-conforming joints, So, hence P chart is a suitable chart. So, how to evaluate this? We have the subgroup number, we have the number of joints welded Ni, we have observed the number of non-conforming units, improper welding, that is Di, compute Pi is equal to Ni by Di, calculate UCL using the formula P bar plus 3 times root of P bar 1 minus P bar divided by Ni. Calculate LCL is equal to P bar minus 3 times root of P bar into 1 minus P bar divided by Ni, where Ni is the joints welded, Di is the number of non-conforming joints. Calculate Di, UCL and LCL for each subgroup. We have the following chart. Middle one is the central line P bar, red dash line is the upper control limit, lower red dash line is lower control limit. Since the sample size is varying from subgroup to subgroup, UCL is not a straight line, it has ups and downs. Similarly, LCL is not a straight line, ups and downs. So, this is the difference between P chart and NP chart. In NP chart, we have a straight line for UCL and a straight line for LCL. In this case, UCL is changing ups and downwards directions. So, first we fix the central line, then plot the UCL, then you plot the LCL, then plot the fraction number of non-conforming units, that is pi values. All these dots are pi values. The red dot indicates the values are going outside the control limits, and inside the points indicate that they are inside within the control limits. If these UCL or LCL are the trial limits, then we have to remove these red points, recompute P bar, UCL and LCL once again, removing the dot points, the points which are going outside the control limits. Repeat the procedure until all the values are within the control limits. Suppose these lines are taken as the final control limits, this will be the final chart. From this we say whether the process is under control or not. This says that the process is out of control because 5 points are going out of control. So, you have to decide whether you are fixing first the trial control limits or the final limits you are choosing for your inspection. Conclusion. In this lecture, we have discussed how to construct control charts for attributes in different situations and how to interpret them. We discussed applications of binomial and Poisson distribution in setting the control limits. We discussed the difference between the control charts for non-conforming units and non-conformities. We also discussed the use of attribute control chart over variable control charts. Thank you.